press record, share the screen, stuff like that. Okay, the quiz is now too late. So if you haven't already submitted the quiz, I'm not taking any more. I mean, you have what, 5 days to do it, Thursday to Tuesday? So plenty of time. Okay, so first one, x ln x, integrate by parts. U equals ln x, dv is x dx. You would rather differentiate the ln than integrate the ln. Okay. So du equals 1 over x dx. V is equal to x squared over 2. So integral is uv minus integral v du. uv is 1/2 x squared ln x minus v du. So 1/2, bring it outside. X squared times 1 over x dx. That comes out to be the integral of x. So you have 1/2 x squared ln x minus 1/2 times x squared over 2 plus c. Final answer, 1/2 x squared ln x minus 1/4 x squared plus a constant. Okay. I'll double check if you differentiate this, you get this back. I'll go ahead and show that to you. This looks like a product rule. First times the derivative of the second, 1/2 x squared times 1 over x, plus second function, ln x, times the derivative of the first. Derivative of 1/2 x squared is x. Derivative of negative 1/4 x squared is minus 1/2 x. The derivative of any constant is 0. So that gives me 1/2 x plus x natural log of x minus 1/2 x. 1/2 x cancels out, x natural log of x. So that confirms that the derivative of this thing is indeed this. Okay, number 2, that u be cosine x, du is negative sine x dx. Okay, you cannot go the other way. If you try to go the other way and let u be sine x, du would be cosine x, but you don't have cosine x, you have cosine squared. Okay, you'd rather let u be cosine. Du is negative sine x dx, put a negative 1 inside and outside. Negative u squared, so negative u cubed over 3, or negative 1/3 cosine cubed x plus c. And finally, number 3, there's actually more than one approach. To me, the easiest approach is to break it down into secant cubed times secant x tangent x dx. Now, some of you did a different approach. You got an answer which seems to be different. It's actually equivalent. Okay, so if you got that other answer that seems to be unrelated, they're actually equivalent. I know that it works out to be the same, but it is a lot cleaner if you said, let me write this as a secant x tangent x, and I have a secant cube. Then I'll just do a u substitution, because the derivative of u, secant x, is secant x tangent x, right? So I just integrate u cubed. U to the 4th over 4, 1/4 secant to the 4th x plus a constant. Okay, so that's it for the quiz. Okay, and Thursday you'll get another quiz. All right, so what is it on? Well, it's got to be stuff that we covered so far. I'm not quite sure yet, but maybe a partial fraction, maybe a trig substitution. So maybe 7.3, 7.4, stuff like that. Okay, but hey, you don't have to study for the quiz anyway, because you can talk about it. I'll put you in your breakout groups, and you have 5 whole days to do it, right? So who could ask for anything more, right? Okay, so that's that. All right, so we are over here. On my original schedule, I was only going to do 7.4. I'm actually almost done with 7.4. So I was going to do 7.7 also. So I've managed to get a little bit ahead again. Again, I'd rather be ahead in case something happens. Well, something did happen. I was down for a week. Okay. Oh, and remember last time my internet was down for a while. The previous class that I had, of which some of you are in there because some of you, for whatever reason, want to take me twice. But the previous hour when I taught, the computer went down again. I'm hoping it doesn't happen again, but we'll see. So I'm going to aim for 7.4 and 7.7, in which case I'll be a day ahead, just in case, quote unquote, something happens again. So we'll see. So I'm on schedule. In fact, I'm a little bit ahead. We'll do a little bit more of 7.4 and do 7.7. Okay. And I think I alluded to this 7.4. I tried to give you a note of that on Canvas, but if not, skip 39, 41, and 43. So we're just doing 1 to 23 odd. And also 7.1, let's skip 21. Now, if you already did 21, great, good for you. It's a much more difficult problem. It has a product on top of a quotient, so it's much more challenging. So 7.1, skip 21. So game plan, I would do some more of 7.4 and then do 7.7. And 7.7, there are only 6 problems, of which I was going to do 3, half. So, you know, I do 3, you do 3. And there we go. Okay, so that's where we're at. So it looks like maybe for Thursday, I can perhaps get started with a 7.8 even. Okay, so I'll be ahead by a day. And then, you know, that'll give you more time to work with each other in the quiz. But I'm not going to change the exam date. So even though I might finish early, our exam will still be Thursday, October the 1st. Okay, and I'll just get ahead in case something goes wrong. I mean, that's what I said last time before I was down for a week, right? So in case things go bad, and if it happened before, it might happen again. And if your internet ever goes down, that's fine. Just let me know. You can always look at the video, and you'll be excused for that. It's already happened to me, a couple of times. All right? All right, so let's get back to some more of 7.4, the partial fractions kind of problems. Okay. Go back and show you 15. It's a definite integral from -1 to 0. X cubed minus 4x plus 1 over x squared minus 3x plus 2 dx. So the first thing you want to do before you start partial fractions or anything else is the degree of the numerator has to be less than the degree of the denominator. And if it isn't, you do polynomial long division. All right, so do you recall polynomial long division? Right, the x cubed stuff goes on the inside, and x squared minus 3x plus 2 goes on the outside. And you might recall when you did long division, when you have x cubed, you have to have an x squared, and if it's missing, count it as a coefficient of 0. So once you put down x cubed, right, you must have x squared, you must have x, you must have a number. So x cubed plus 0x squared minus 4x plus 1 divided by x squared minus 3x plus 2. Okay. Well, in an extreme case, let's suppose you just have x to the 7th minus 1. You have x to the 7th minus 1. In here, you got to have x to the 7th plus 0x to the 6th plus 0x to the 5th plus 0x to the 4th plus 0x cubed, x squared, x, and then finally the minus 1. So anything that's missing, count it as a coefficient of 0. Okay, so x cubed plus 0x squared minus 4x plus 1. All right, then the rest is polynomial long division, as you might recall. So I look at the first thing here and the first thing here. What do you multiply this by to get this? How do you go from x squared to x cubed? You multiply by x. So I put the x over here and line it up. Notice there are separate columns. This column is reserved for x cubed. This is all x squared. This is all x, and this is all numbers. All right, now what's x times this whole thing? X times x squared is x cubed. X times negative 3x is negative 3x squared. X times 2 is 2x. Subtract. That minus that is nothing. And remember, you have to be careful. It's a subtraction. 0 minus a negative 3, that's 0 plus 3, so positive 3x squared. Negative 4 minus 2 is a negative 6x. And then bring down to 1. And then just do it all over again. Repeat the process. So look at the first thing here, first thing here. What do you multiply x squared by to get 3x squared? 3, positive 3. Now you go 3 times this whole thing. 3 times x squared, 3x squared. 3 times a negative 3x, negative 9x. 3 times 2, 6. Subtract. 3x squared minus 3x squared is nothing. Okay, watch out for all the negatives. Negative 6 minus a negative 9. Negative 6 plus 9, 3x. 1 minus 6 is a negative 5. Okay, this is considered my remainder. So my original integral, which was this, I can now write as x plus 3 plus the remainder of 3x minus 5 over x minus 1, x minus 2. Okay, this is easy to integrate. This is easy to integrate. This looks like partial fractions. So it's now like you have to take a time out and figure out this partial fraction decomposition. Is that right? So here we go. This is case 1, the easiest case scenario. Remember we had those 4 cases? You had a linear with no repetition. That was case 1, the easiest. This is the so-called easiest case. Okay. Case 2, you had a repetition, like maybe an x minus 1 squared. Case 3, you had irreducible quadratics, like x squared plus 1, in which case you need a linear expression on top. And then case 4, the hardest, where you have irreducible quadratics repeated. Right? And anything that long, I probably wouldn't have you do the whole thing unless it turned out to be very easy. Good. And yeah, the problem I was going to show you after this actually has a case, or a different case. I forgot which situation it is. Oh, it has an irreducible quadratic. So I'll show you that one. It's much longer. All right, so we know what to do. A over x minus 1, b over x minus 2. Okay? And even at this stage, regardless of what a and b turn out to be, you can tell it's going to be integratable, right? I can integrate. Suppose a is 7, b is negative 4, or whatever. This is going to be 7 ln absolute, and then minus 4 ln absolute. And we already know how to integrate that and that, right? All right, so here we go. A over x minus 1, b over x minus 2. I need a common denominator. The left side, I need to multiply by that, x minus 2 over x minus 2. The right side, I need to multiply by that, x minus 1 over x minus 1. So now I have my common denominator, x minus 1, x minus 2. Multiply out the top, ax minus 2a plus bx minus b. Then I gather like terms. Gather the x's. These two are x. So write it as a plus bx. And these two don't have any x. They're considered constants. Negative 2a minus b over x minus 2, x minus 1, x minus 2. All right, so what am I ultimately aiming for? I want that to equal this, 3x minus 5 over x minus 1, x minus 2. So how can I get this thing to match this? Well, you already have the bottom the same. I just got to make the top the same. That means this stuff better be 3x minus 5. It's coefficient times x. That coefficient better be 3. I mean, it's not going to be equal if this is a 4 or a 2. This better be equal to 3. And my constant means there isn't any x. This constant better be a negative 5. It can't be a negative 4. It can't be a negative 6. It better be negative 5. So a plus b equals 3. A plus b equals 3. And negative 2a minus b has to equal negative 5. There it is. Okay, 2 equations, 2 unknowns. And you can solve it by substitution or elimination. Here, elimination is pretty easy. If you add them up, b drops out immediately, right? So just add straight down. B's are gone. Negative a equals negative 2, which means a equals 2. And plug back here. If a is 2, then that means b is 1, right? 2 plus b equals 3, b equals 1. So I found my a and b are 2 and 1. So now I can replace this expression with a 2 and a 1. So it's 2 over x minus 1, 1 over x minus 2. Is that right? Okay, so finally, at long last, look at the progression. We started off with this pretty bad looking rational expression. I can write it now, x plus 3 plus all that, which I now have found to be 2 over x minus 1 plus 1 over x minus 2. And now I can integrate the whole thing. That's easy. That's easy. That's some ln. That's some ln. Okay? All right, so here we go. Integral of x, x squared over 2. Integral of 3, 3x. plus 2 ln absolute value of x minus 1 plus 1, well, if it's 1, you don't have to write the 1, ln absolute value of x minus 2 from negative 1 to 0. So paren, plug in 0. Paren, plug in negative 1. 0, that's 0, that's 0. 0 plus 0. If you put a 0 here, it's ln absolute value of negative 1. Absolute value of negative 1 is 1, and natural log of 1 is 0. So all of these are 0, but not this one. If you put a 0, you're taking natural log of absolute value of negative 2. Absolute value of negative 2 is 2, so ln 2. Okay, minus. Now the harder one, plug in negative 1. So negative 1 squared is 1, so 1/2. Put a negative 1 there, that's negative 3. Put a negative 1 there, that's negative 1 minus 1 is negative 2, whose absolute value is 2, so 2 ln 2. And put a negative 1 there, you get ln absolute value of negative 3. Absolute value of negative 3 is 3. Okay, so I clean it up. These are nothing. ln 2, distribute minus 1/2 plus 3 minus 2 ln 2 minus ln 3. Okay, so what did I do next? These two, negative 1/2 plus 3 is 2.5, right? 5 over 2. These two, natural log of 2 minus 2 ln 2, that's negative ln 2. That's basically 1 minus 2. And then minus ln 3. Okay, and to clean it up a little bit more, I put 5/2 minus parentheses ln 2 plus ln 3. Right? Distribute minus that. And we know that ln 2 plus ln 3, one of the properties of log is the ln of 2 times 3, or ln 6. So here's the best final answer. 5 over 2 minus natural log of 6. And that's that. Okay, so that was 15. And the other one I wanted to show you was problem, what? 23. Okay. But before doing 23, I need to review one other thing with you. Okay, so do you recall this integral? What's the integral of 1 over 1 plus x squared? Another way to think about it is think back to your Calc 1. The derivative of what function came out to be this? Inverse tangent, you might recall. Right? The derivative of inverse tangent was 1 over 1 plus x squared, which means the integral of 1 over 1 plus x squared is inverse tangent. Okay, so we need to use that. Right, so problem 23, and then I was basically done with the section. By the way, we may finish early today. If that's the case, then I'll stop and let you ask a bunch of questions if you wish. 10 over x minus 1, x squared plus 9. Okay, x squared plus 9 is an irreducible quadratic, you might recall. Okay, so over x minus 1, x squared plus 9. Okay, and a side note here, the degree of the denominator, what's the degree of the denominator? If you multiply it all out, third degree, you have x cubed. Which means on top, you could have anything up to x squared, and it works. There is no x squared, counted as a 0. There is no x, counted as a 0. Okay? So pretend the top is 0x squared plus 0x plus 10. I'm not going to write it because we use it a little bit later on. Oh, I got it way down here. Okay? But you know that's the same as 0x squared plus 0x plus 10. All right, so how do I break this one up? X minus 1, x squared plus 9. Okay, so 10 over x minus 1, x squared plus 9. Okay, so x minus 1, x squared plus 9. Okay, now, if this had been x squared minus 9, you would keep factoring, right? You would go x plus 3, x minus 3. but x squared plus 9 is an irreducible quadratic, which means what goes on top? A linear expression. So x minus 1 being linear, you just put an a on top. But x squared plus 9 needs a bx plus c. Ignore that 1, -1, and -1 for now. Pretend you don't know it. But that's going to be the answer to this a little bit later. All right, so one more time. If you have an irreducible quadratic, that was so-called case 3 that I showed you last time, then you need a linear expression on top, bx plus c. So this is going to be maybe the hardest one that we've had so far. So a over x minus 1, bx plus c over x squared plus 9. Need a common denominator. So what does the left side need? X squared plus 9 over x squared plus 9. What does the right-hand side need? X minus 1 over x minus 1. Okay, so now x minus 1, x squared plus 9. Multiply all this junk here out. So ax squared plus 9a. And these look like FOIL, right? So bx squared minus bx plus cx minus c. Okay, now I gather like terms, meaning gather the x squareds together, the x's together, and the constants together. Okay, so what do I mean by that? So where's all the x squareds? Excuse me. Here are the x squareds. If I factor that out, it'll be a plus b x squared. See that right over here? So these two combined, ax squared plus bx squared, right? Factor out the x squared, a plus b. Now the x's are here and here. These two have only x. So parentheses negative b plus c x. And then the constants. Constant means there's no x. This one doesn't have any x. This one doesn't have any x. So 9a minus c. Okay. Quick double check. Let's multiply this out. Ax squared, there it is. Bx squared, there it is. Negative bx, there it is. Plus cx, there it is. And 9a minus c. Or double check. 1, 2, 3, 4, 5, 6 terms. 1, 2, 3, 4, 5, 6 terms. All right, I want it to equal 10, and 10 is equal to 0x squared plus 0x plus 10. So that's what we're talking about right now over here. Okay, 0x squared plus 0x plus 10. So now I want a plus b to be 0, matching coefficients of x squared. I want negative b plus c to equal 0, matching coefficients of x. And I want 9a minus c to be equal to 10, matching the constants. So I will have 3 equations in 3 unknowns. Okay, so a plus b equals 0. Negative b plus c equals 0. And finally, 9a minus c is equal to 10. Okay, so you can solve that in a variety of ways. Let's see, if I move the b over, then b equals c. Agree? If negative b plus c equals 0, if I add b to both sides, that means c and b are equal, which means a and b are opposites. Right? Just subtract b over, a is equal to negative b. And that also means that a is equal to negative c. Okay, so one more time. If I move b over, b and c are equal. And if I subtract b, a is equal to negative b, which also means a is equal to negative c, since b and c are equal. Okay, so that means right here, see this negative c? I can change it to a. All right, 9a minus c is 9a plus a. Right here. Negative c, change it to a. 9a plus a, 10a. So 10a equals 10. A is equal to 1, which means c is negative 1, and b is also a negative 1. All right, so that's what I meant over here now. So a is 1, b is negative 1, c is negative 1. By the way, we're far from being finished. Okay, there's still a lot more to this problem. All right, so now I'm going to have 1 over x minus 1, and then all this stuff. So 1 over x minus 1 minus x minus 1 over x squared plus 9. Okay. I'm deciding because I have a negative negative, it's a lot cleaner if I go minus x plus 1 over x squared plus 9 like so. Okay, so do you agree this is the same as this, but this looks a little bit cleaner. This is easy. This is just some natural log. Okay, now, how do I integrate this? I split this into two integrals. So I break this up, which in retrospect I didn't have to do here, but anyway, it works. So minus x over x squared plus 9 minus 1 over x squared plus 9. So I have three integrals. I'm going to take a timeout and work on I1 minus I2 minus I3. So the original integral I is I1, I integrate 1 over x minus 1, minus I2, which is x over x squared plus 9, minus I3, which is 1 over x squared plus 9. This is just going to be some ln. This looks like it's going to be a u substitution. The derivative of the bottom is almost the top, except for a constant. This is going to be a variation of inverse tangent. Okay. If it was x squared plus 1, it's perfect for inverse tangent, but there's a 9 there. Okay. The way to get around a 9 is to force this to be a 1, and I'll show you how to do that. Okay, so now I will say I, the original integral, is I1 minus I2 minus I3. Okay, so once I figure out I1, I2, I3, I put them all together. All right, so here's my I1. Integrate 1 over x minus 1. That's ln absolute x minus 1. And notice again, plus C1. There's a C1, a C2, and a C3. But in the final answer, when you have C1 plus C2 plus C3, that can all just be put together as one C. Okay, I2. Ignore the red temporarily. X over x squared plus 9 dx. The derivative of the bottom is the top except for 2. That's okay. You can put constants in and out. So u equals x squared plus 9, du equals 2x dx. I cannot substitute until I have a 2 here. So 2 inside, 1/2 outside. By putting these two things in red, I have multiplied this integral by 1, which means I don't change its value. So now all of this, 2x dx, becomes my du. X squared plus 9 is u. So that gives me 1/2 du over u. That's my natural log. You can pretend there's a 1 here, right? 1 over u. 1/2 ln absolute value of u plus C2. Change u back. Now, here's another rule. Notice I didn't put the absolute value in my final answer. And you should do the same thing for this particular problem. How come I don't put absolute value? Because what do you know about x squared plus 9? The sign, SIGN, of x squared plus 9 is always positive, right? You cannot have this to be a negative expression or 0. Okay. If I just have x squared, what's the smallest x squared can be? 0. If I plug in any other real number, it's positive. Now I'm going to add 9. If you add 9, it's dead sure positive. So since I have a positive quantity, I don't need the bars anymore. I put parentheses. And again, I'll be stronger. You should just put parentheses. So 1/2 ln x squared plus 9 plus C2. Now for I3, I haven't shown you anything like this before. So this is brand new. 1 over x squared plus 9. All right, now there's an x squared. What you want to do is force this to be a 1. Because if it's 1 over 1 plus something squared, we know what to do. Okay, so when it's like this, I factor out the 9. So I put 9 in front, 1. So there's the one that I want. Plus x squared over 9. How do I get x squared over 9? Well, when you put the 9 there, you end up multiplying by 9. So to balance, and you end up with only x squared, you divide by 9. Okay. Or what answers the question always is, what do you get when you multiply it back out, right? What's 9 times 1? 9. What's 9 times x squared over 9? Well, the 9's drop out, so you have x squared. So this is indeed the same thing. Okay, so now what I'm going to do is take the 1/9 outside. 1/9 is outside. And I want to write this as 1 plus something squared. 1 over 1 plus. So what do you square to get x squared over 9? What object times itself is x squared over 9? X over 3. Okay, ignore that red, ignore that red. So right now I have 1/9 dx over 1 plus x over 3 squared. Then I'll do my u substitution, because this is going to be 1 plus u squared. Okay, and I know how to integrate 1 plus u squared. That's my inverse tangent. So u equals x over 3, which you should think of as 1/3 x. du equals 1/3 dx. Okay, so before I substitute, I need a 1/3. So 1/3 inside means 3 outside. 3 times 1/3 is 1. So I have an equivalent expression. All right, so I3, I have 1/9 times 3, which is 1/3. dx times 1/3. dx times 1/3, I can now substitute with du. 1 plus x over 3 squared. X over 3, or 1/3 x, is u squared. And now this is ready for my inverse tangent. Okay. Strictly speaking, the inverse tangent had a 1 here, but you can always sneak in the 1, right? Put the 1 there. So 1/3 inverse tangent of u plus c3. Change inverse tangent back to what it was. It was x over 3. 1/3 inverse tangent of x over 3 plus c3. All right. So finally, way back here, I was I1 minus I2 minus I3. Here's my I1. Put that there. Here's my I2. Whoops, where'd it go? Here. There's my I3. Put them back in. So I1 was ln absolute value of x minus 1 minus I2, which is that, 1/2 natural log x squared plus 9 minus I3, 1/3 inverse tangent of x over 3. And then you have C1 minus C2 minus C3. Then you can just put plus C. All right, so finally, that's my answer for this particular one. Okay, and while you're looking at that, I am going to say there is a shortcut mentioned in the text. Okay, I'm not going to let you use it. Okay, so you might look at it and say, hey, why don't I just do that? You can't do it. So anytime you have this kind of inverse tangent, I want you to be able to show me this strategy here. So 1 over x squared plus 16, 1 over x squared plus 4, or whatever. You might say, hey, the book has a rule. Here it is. Page 497, right here. Here's the rule. But my rule is you don't get to use it. Okay, so if you go straight from here to here, you will lose points. Lots of points. You got to show me all of this stuff. Okay, so you've been warned. Okay, I want you to be able to show me that you can do all this stuff over here. Okay. All right, that's it for 7.4, folks. So that's all I was going to do. It's about 10 minutes to 8. Okay, I'm going to give you an introduction to 7.7, but I won't do any problems until after the break. Okay, so I'm finished with 7.4. I wasn't supposed to start 7.7 until next time, but I will, so we're a little bit ahead. Okay, and again, the assignment for 7.7 is to just do these, of which I'm going to do 3 of them. Okay, right now, we don't even know what it means, so we'll see. Okay, so skip 7.5, skip 7.6. 7.7 is on approximate integration. All right, so right now we have all these different techniques of integration, and yet there are still some integrals that we can't do. In fact, even today, this very day, September 22nd, 2020, there are some integrals that nobody knows how to do. In fact, some of them have been proven not to be able to be done at all. You just can't integrate it. In fact, I'll just go ahead and tell you. e to the x squared, you cannot integrate that. It's been shown it's impossible to integrate that by conventional means. Okay. And when I say by conventional means, we're actually going to be able to do it in our last chapter, chapter 11, but we don't even know what that means yet. So don't worry about it now. But if you tried integral of e to the x squared dx, guaranteed you can't do it. You can try U substitution, trig substitution, partial fractions. Oh, there is no partial fractions here. You won't be able to find the integral of e to the x squared. Which means the only thing you can do is approximate integration. Okay, so what is this approximate integration stuff? Okay, so in this section, there are going to be 3 rules. One of them, I think you already know from Calc 1, midpoint rule. Okay, now it's on page 515. Do you have to write this down? I don't think so. I'm going to give you a condensed version of the midpoint rule, so I'll give you the Melvin Hum version. Okay, but I think you saw that in Calc 1. Okay, if you want to approximate the area under the curve, chop it up into so many pieces. Like here, n is equal to 4, right? So we're reviewing this from Calc 1. Go like that. Midpoint rule says that on each subinterval, take the midpoint, right? So that one's in the middle, that one's in the middle, that one's in the middle. Go straight up until you touch the curve, draw a rectangle. Go straight up, draw a rectangle. Go straight up, draw a rectangle, right? Then just add these up. Now you might say that's not fair. You're exactly right. That's why it's only approximate integration. So we're cheating. Instead of the real area under the curve, I'm taking the area of this rectangle plus the area of this rectangle plus the area of this rectangle plus the area of this rectangle. And you say, surely they don't have to be the same. And you're right. Most of the time, they're not going to be the same. Okay? I mean, look over here at the first rectangle. This piece isn't supposed to be there, but I was supposed to get this piece. Do they exactly cancel out? Maybe yes, maybe no. And let's say this last rectangle, right? Okay, this extra piece wasn't supposed to be there, but I was supposed to have this piece, right? So do they match? Probably not, but that's what's going on for a midpoint rule. So for the midpoint rule, instead of taking the area under the curve, you approximate it with rectangles. Okay, a little bit of theory. Then we have something called the trapezoidal rule. Trapezoidal rule is on page 516. Here's the rule. It's correct. Do you have to write it down and memorize it? No. Again, I'll give you my version of it in a little while. Okay. Do you remember what a trapezoid looks like? Okay, trapezoid has how many sides? 4 sides. One pair of opposite sides is parallel, but the other is not. Okay. Like here are some trapezoids. Here's the idea behind the trapezoid rule. Okay, so take the area that you want to consider, like this one or this one. Chop it up into so many pieces. So here's 1, 2, 3, 4 pieces. 1, 2, 3, 4, 5 pieces. But instead of making rectangles, just take this point and draw a straight line segment. Okay, to this point and this point, straight line segment. Same thing here, same thing here. You can see the approximation looks pretty good, right? Same thing here. In fact, this looks very good, somewhat. Okay, so instead of taking the midpoints, just take this top point and this point, just connect them with a straight line segment. Do the same thing from there to there, there to there, there to there, there to there. You take a look at this. This looks very good, right? It looks almost like the true area under the curve if I do trapezoids. They're just trying to show you here what would happen if you did the midpoint rule, right? So if you did the midpoint rule, you can see, you lose some and you gain some, right? So that white space there, I should have under the curve, but I gained this extra piece here that I was not supposed to. Same thing here and here and here and here. This looks pretty good, right? Trapezoidal rule. Right? There is a formula for the area of a trapezoid. We're not going to worry about it, but in case you got to know, you basically average these two bases multiplied by the height, which kind of makes sense. Okay, so we have these two as bases. The height is the distance from here to here, let's say. If I took this distance, that's too small. If I took this distance here, that's too big. So you average the two. Very logical. So you average these two, okay, which means you add them up and divide by 2 and get the height. Okay, we won't go through the derivation, but this is what the formula comes out to be. Looks like this. I'm just going to show it to you real quickly. You don't have to write this down. I'll give you the Melvin Hum version shortly. That's trapezoidal rule. Okay, the last approximation is something called Simpson's rule. So there's a mathematician from many years ago. Simpson was his name. 1800s, I believe. Whatever. Now, for Simpson's rule, you have to have n be an even number. The number of pieces that you chop this up into has to be even. Very conveniently, all the n's that I've given you are even. Now, for the midpoint rule and the trapezoidal rule, n's allowed to be odd. Simpson's rule, you have to have an even number. As you can see, they're all even, so we're good. So here, they've got 1, 2, 3, 4, 5, 6 pieces, actually. They split into 6. Here's the strange game we're playing now. Take these 1, 2, 3 points, that one, and the one in the middle. Draw the best parabola that goes through those 3. So in red, they have a parabola. Keep doing that. This point, and the one in the middle. Draw the best parabolic approximation, parabola. By the way, you can always do this. Okay? If you take any 3 points, if you take 3 points at random, stop and think about it. Okay? Take these 3 points. Can you see a parabola? Okay, right? You can kind of visualize something like that. Or maybe I have 1, 2, 3. Can you see such a parabola? Maybe we'll go something like this. Okay. And that's true. You'll always be able to draw a parabola, well, unless you have a straight line. If you have a straight line, then you just draw the straight line. Okay. But yes, you can prove that you can always come up with a parabola. So what's happening in Simpson's rule, in case you're wondering, do you have to write anything down? No. Okay. You're replacing the curve with another curve, a parabola. What does a parabola look like? Well, since it's second degree, it's of the form ax squared plus bx plus c, and we know how to integrate ax squared plus bx plus c. X squared becomes x cubed over 3, x becomes x squared over 2, c becomes cx, and so on, right? So I replace the actual points in the graph with a parabola. It's a curve. And these 3, the best parabolic approximation, and these 3, the best parabolic approximation, something like this. Okay, so I integrate all of that stuff, okay, and then we come up with a rule. Okay, I won't go through the mathematical derivation of that, but you replace the actual integration with a parabola. Okay. So we have 3 rules: the midpoint rule, if you want to look at it in the text, it's 515. Trapezoidal rule, 516. And Simpson's rule. So we want to see Simpson's rule. Page 520 at the bottom. Here's the rule. Again, don't really look at it. I'll give you my version, which is equivalent. Okay. And normally, I would spend the time to show you the problems. Well, I didn't like any of the problems, so I don't have to really show you any of this. Okay. And you already have all of this. Right? So there we go. Okay, so here is my version of the midpoint rule, trapezoidal rule, and Simpson's rule. Okay, so here we go. It's being recorded, so if you don't want to write this down, you can just look at the video later. Midpoint rule, trapezoidal rule, Simpson's rule. Okay. The midpoint rule uses rectangles. Trapezoidal rule uses trapezoids. Simpson's rule uses parabolas. Okay. Can you guess which one will be the best approximation? The best approximation is almost always Simpson's rule. You can make up a picture of where the midpoint rule is best. You can make up one where the trapezoidal rule is the best. But if you just take random functions, generally the Simpson's rule is best for a good reason. It's the only one that's based on curves. Rectangles are straight, right? All straight lines. Trapezoids are all straight lines. But Simpson's rule is the first approximation where you try to account for the curve with another curve. So usually the Simpson's rule is the best rule. All right, abbreviation, MN, TN, SN. M stands for midpoint, T for trapezoidal, S for Simpsons. N is a number of subintervals. So you're chopping it up into so many pieces. Okay? So for number 1, you chop it up into 4 pieces. Number 2, chop it up into 8 pieces. Number 3, chop it up into 6 pieces, and so on. So MN, if N is 4, we would say M4, or T6, or S8. Okay, here's what I want you to know. Okay, and you can write this on your cheat sheet. Now, frankly, if you want to write that super long one that was in the book, you can, but I think you can just get by with this on the test. Okay, so delta x over 1, 2, 3. Easy as 1, 2, 3. Delta x over 1, delta x over 2, delta x over 3. Okay, and yeah, you don't know what this means yet, but once I start doing it, you'll get it. So this one just put a bunch of ones. 1, 1, 1, dot, 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 1. Trapezoidal rule, delta x over 2, 1 at the beginning, 1 at the end. The middle is all 2s. 2, 2, 2, 2, 2, 2, 1. Simpson's rule, Sn, delta x over 3, 1 at the beginning, 1 at the end, and then you alternate 4, 2, 4, 2, 4, 2. If you do it the right way, the second to the last one is also a 4 and then a 1. That should work if n is even. Remember, you cannot do Simpson's rule if n is odd. You have to have an even number. Okay. And again, if we were meeting face to face, like the last time I taught this course, Calc 2, I made my class memorize this. But since you're taking me now under COVID, you get it easier, so you can put this on your cheat sheet if you want. Okay, so midpoint, trapezoidal, Simpsons, delta x over 1, delta x over 2, delta x over 3. These are all 1s, 1, 1, 1, 1. This one, you start with a 1, end with a 1. In between are all 2s. Simpson's rule, start with a 1, end with a 1, and then in between you alternate 4, 2, 4, 2, and so on, 4, 2, 4, and then a 1. This one should never be a 2 if you do it the right way. This one should be a 4. This one should be a 1. Okay, these turn out actually to be multiplication factors. Okay, you're going to multiply by 1. And of course, when you multiply by 1, you just leave it alone. And you already know how to do the midpoint rule, right? You've done midpoints in Calc 1. Remember in Calc 1, you probably did left endpoints and you did right endpoints and midpoints, right? So we're just rehashing midpoints. Okay, what's all this 1 stuff? Essentially, you're multiplying all the expressions by 1, which means you don't do anything. So it's a multiplication factor. Here, you're multiplying the first and the last terms by 1, but all the in-between ones get multiplied by 2. Yeah, I know this is still all fuzzy. You don't know what it means now, but just the fact that I'm saying it will help. Then for Simpson's rule, you multiply the first and last ones by 1, and then the in-between multiplication factors are 4, 2, 4, 2, 4, and so on, and then 1. Okay, so you want to put all of this stuff on your cheat sheet, preferably. Okay. All right, but I guess it's a good time to break. So let me stop the share, and we will break. And I think what I'll do from now on to make sure the videos are okay is I won't actually pause the recording. So we're going to record even the break, but that way, that's the only way I can be sure that everything's going to work out. Okay, so we'll break until 8:15. Okay, so 8:15 we'll break, but we're still recording per se. All right, thanks. Start up again at 8:15-ish. All right, folks, it's time, so let's try to get back to where we were. Okay, so we're still recording, in theory. Okay, question was brought up about this formula that I wasn't letting you have per se. Now, technically, if you want to write it, you may. Okay? It's just that you can't use it. Okay, so I mean, that sounds weird, but you don't need this because I'm not letting you use it as how to solve problems. Okay, so in other words, if you have integral of x squared plus 9 or x squared plus 25, okay, you can put this formula if you wish, but you're wasting space, I guess is the way to say it, because I want you to be able to show me the technique that we did in class, okay, where you would factor out, I think it was x squared plus 9, so you factor out the 9 and make it x squared, 1 plus x squared over 9, which becomes x over 3 quantity squared. Okay, so in other words, I don't want you to go straight from here to here. So technically, you can put it on your cheat sheet, but it doesn't help because you're not allowed to use it. You need to show me the way we did it in class. Okay, so hopefully that takes care of that. All right, so what I was going to show you were, let's see, what was I going to show you? Number 1, number 2, and number 4. 1, 2, and 4. And that's basically it, in which case you do 3, 5, and 6 on your own. And if we finish early, fine. Then I'll turn it into an office hour where you can ask questions. And if nobody asks questions after a while, we can just stop. Okay. So then Thursday, it's looking like I might even be able to get started with 7.8. Okay. Because I was only planning to show you 3 problems. I might be able to do all 3 problems tonight. And then you do the others, and then I'll be a day ahead. Like I said, in case something happens again and I lose a day, or computer goes down, or I get sick, or whatever. Okay, so we're still aiming though for October 1st. So no matter what, I don't plan to change the date of the exam. We're still going to have it on this day. Okay. All right, so let's get started with approximate integration. So we're using these things here, right? Y equals e to the x squared between 0 and 1, n equals 4. Okay. Number 2, y equals x cubed between 1 and 2 for n equals 8. All right, now here's the way I'm going to present the material. Okay, for both 1 and 2, I'm going to do both midpoint rules. Then I'll do both trapezoidal rules. Then I'll do both Simpson's rules. Okay, I think it's easier if I present it that way. And then when I do number 4, I'll do them all at the same time. Okay, so the graph is e to the x squared between 0 and 1, n equals 4. We're approximating the integral. So let me show you the picture. Y equals e to the x squared. Okay, again, this is something that you can't integrate by normal means. So is there abnormal means? Yes, there is. We'll see that in our last chapter. Between 0 and 1, chop it up into 4 pieces. All right, now, you don't have to graph the functions. I did just for this first example, but it's not necessary. Okay? After a while, I didn't bother graphing it. Well, for number 2, I didn't bother graphing it. But you know what x cubed looks like, for sure, right? But you normally just need a number line, but we don't have to graph the whole thing. But for this first example, I will. So here's 0, here's 1. What do you get when you plug in 0? 1. What do you get when you plug in 1? E. So 0, 1, 1e. It's an increasing function like so. Okay, now I'm going to go fairly fast over the calculations because all you do is just punch everything in your calculator. You can do it as well as I can. But you should, go check on your own that you're getting the same numbers that I'm getting when you're doing all this stuff. Okay, chop it up into 4 pieces, n equals 4. So if I'm going from 0 to 1, and I chop it up into 4 pieces, what is my delta x? Well, 1/4, 0.25. Okay, so one more time, I'm going from 0 to 1. That's 1 unit, right? So from here to here is 1. You're dividing it into 4 equal pieces. So it's 1/4, 1/2, 3/4, and 1. So delta x is 1/4 or 0.25. Okay, what are we doing? We're approximating the integral of e to the x squared dx. You cannot do this by usual means. Okay, so you can try substitution, trig substitution, whatever. Can't do it. Okay, I will say if there was an x in front, x e to the x squared dx, that's a simple use substitution because the derivative of x squared is 2x, and you have the x, you can just put the 2 inside and a half outside. Okay, but you can't do this by usual means. It can be done by unusual means. We'll get to that in our last section, chapter 11. Okay, so how does a midpoint work? You got to find all the midpoints. So here are the endpoints: 0, 1/4, 1/2, 3/4, and 1. So what's all the midpoints? And the easiest way to find the midpoints maybe is to think of all of these as 8s. Think of this as 2 8s, 4 8s, 6 8s, 8 8s. So what's halfway between 0 and 2 8s? 1 8. What's halfway between 2 8s and 4 8s? 3 8s. What's halfway between 4 8s and 6 8s? 5 8s. And what's halfway between 6 8s and 8 8s? 7 8s. So the midpoints are 1 8, 3 8, 5 8, 7 8. Okay, so now in Calc 1, you probably did something like this. Go straight up, draw a rectangle. 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 And then you go base times height, base times height, base times height, base times height. Well, all the bases are the same. They're all 1/4. And then the heights are just the function values at the midpoints. Okay, so notation, M4. M stands for midpoint. 4 is the number of pieces you're chopping the picture up into. Chop it up into 4 pieces. Okay, so it's delta x. By the formula that I showed you, it was delta x over 1. Right? Remember that sheet that I showed you? Delta x over 1. And then it was all 1s, 1, 1, 1. It means you're multiplying all of these by 1, which means you don't do anything. So f of 1/8, f of 3/8, f of 5/8, f of 7/8. Okay? So I plug in 1/8, 3/8, 5/8, 7/8 into the function, which is e to the x squared. Okay, so just before the break, it was delta x over 1, which means I just leave it as delta x. And then remember, we got 1, 1, 1, 1, 1. It means multiply these by nothing. So just leave it as 1. F of 1/8, f of 3/8, f of 5/8, f of 7/8. Okay, so the function is e to the x squared. So I square all of these. 1/4, e to the 1/64th, e to the 9/64ths, e to the 25/64ths, e to the 49/64ths. I'm squaring all of these, right? You square that, square that, square that, square that, and they become the exponents floating up here. Okay, now you just punch all of that in your calculator, and I'll save time and just tell you what you get. Okay, and yeah, we're supposed to round to 6 digits. That was the directions in the actual text. I didn't put it here, but let's go ahead and say 6 digits. Round to 6 digits to the right of decimal point, because that's what they did for the regular 7.7 homework. So 1.448746 was the approximation. Okay. That's it. And I think you've done that before. Okay, problem 2. I'm only doing the midpoints. We're going to come back for trapezoidal rule and Simpson's rule. So admittedly, when you look at this, it looks like there's only 6 problems. It's really 6 times 3 or 18 problems, which is more like it, I guess. Because for each one, you're doing a midpoint rule, then a trapezoidal rule, then a Simpson's rule. Okay, still midpoint rule. Y equals x cubed from 1 to 2, n equals 8. So you're chopping it up into 8 pieces. So how far is it from 1 to 2? Well, 1 unit. Divide into 8, so delta x is 1/8. All right, so this is 1 and 1/8, 1 and 2/8, 1 and 3/8, 1 and 4/8, 1 and 5/8, 1 and 6/8, 1 and 7/8, 1 and 8/8. And now to get the midpoints, the 1, 2, 3, 4, 5, 6, 7, 8 midpoints. Well, it's a little bit tough, but think of all of these as 16ths now. So in other words, think of this as 1 and 2/16, 1 and 4/16, 6/16, 8/16, 10, 12, 14, 16. Then you can tell right away, I hope, what the midpoints are. So what's halfway between 1 and 0/16 and 1 and 2/16? Well, 1 and 1/16. And what's halfway between 1 and 2/16 and 1 and 4/16, 1 and 3/16, and so on. So all the way down the line. So the midpoint rule is delta x, or delta x divided by 1, which is still 1/8. And then the function value at the 1, 2, 3, 4, 5, 6, 7, 8 midpoints. So the midpoints are 17/16. 1 and 3/16 is 19/16. And after that, you basically just add 2 to the numerator. So f of 21/16, f of 23/16, 25, 27, 29, and finally f of 31/16. Okay, a quick double check. That is 1 and 15/16, which is what it's supposed to be. This is 1 and 14/16. 2 is 1 and 16/16, is it not? So halfway would be 1 and 15/16. Okay, so I have 8 midpoints. 1, 2, 3, 4, 5, 6, 7, 8 midpoints. Plug it in the function. The function is x cubed. So I cube these 8 midpoints. Okay, so M8, which means midpoint rule, chop it up into 8 pieces. It's 1/8 times 17/16 cubed plus 19/16 cubed plus 21/16 cubed plus 23/16 cubed, and so on. 25/16 cubed, 27/16 cubed, 29/16 cubed, 31/16 cubed. Punch it in your calculator. You can do it as well as I can. I'll just give you the final result. Now, you want to go back and check that this comes out to be what I have also. So don't just take my word for it, punch it all out. And besides, I've been wrong before, and I'll be wrong again. I might have typed it in wrong sometimes, but anyway. So punch all this in. 3.444318 is what I got. So there we go. So that's our approximation using midpoints. Okay, and a little side note. Here we chopped it up into n equals 4. How many midpoints are there? 1, 2, 3, 4. 4 midpoints. N equals 4, 4 midpoints. N equals 8. How many midpoints were there? 1, 2, 3, 4, 5, 6, 7, 8. So you will have as many midpoints as your n. So n equals 8, 8 midpoints. N equals 4, 4 midpoints. N equals 20, 20 midpoints. I would never have you do something that big. Yeah. You might think that's kind of trivial. Well, of course it's going to be the same. It's actually not going to be the same for the trapezoidal rule and Simpson's rule, which is what I'll show you right now. Okay, so that's that. The problem is finished, but I'll dig a little deeper. We actually can integrate this function, right? We know how to integrate this, so we can tell how good our approximation was. We don't know how to integrate this right now. So the only thing we're allowed to do is this approximate integration. We can't figure this one exactly, though. Okay, so we're estimating the integral from 1 to 2 of x cubed. So that's easy. X to the 4th over 4 from 1 to 2. Plug in 2. 2 to the 4th is 16. 16 divided by 4 is 4. Plug in 1, you have 1/4. 4 minus 1/4, 3 3/4, or 3.75. Okay, so we know the true answer is 3.75. What do we get by our approximation? 3.44. Okay, so it's kind of close. not real close, but sort of close. And you might recall from Calc 1, you could make the approximation better and better if n got bigger and bigger. Right? Then, of course, you probably want to use a computer program to do it, not just do it by hand. But suppose you chop this up into 1,000,000 pieces, right? Let n be 1,000,000. I would suspect that the answer would be very, very, very close to 3.75. Okay, so that's the midpoint rule, something you've already seen from Calc 1. Now new stuff, trapezoidal rule, Simpson's rule. So going back to problem 1, same problem, same picture, same n, same function, same thing for Simpson's rule, right? Same function, same interval, same n, but we're doing it by a different method. Okay, so let me give you the idea behind a trapezoidal rule. Okay, so same picture here, 0, 1/4, 1/2, 3/4, 1. Notice we don't need any of the midpoints. So no midpoints for trapezoidal rule. When we get to Simpson's rule, no midpoints either. So only one of the rules do you need the midpoint. Guess which rule do you need the midpoints? Midpoint rule. Rather obvious, right? So when do I need to use the midpoints? Only the midpoint rule. Not for the trapezoidal rule, not for the Simpson's rule. You just use the endpoints. These 1, 2, 3, 4, 5 endpoints. All right, so for T4, you use delta x over 2. Okay, there are 1, 2, 3, 4, 5 endpoints, which is one more than you had over here. And by the way, you're doing the same thing for Simpson's rule, the same 1, 2, 3, 4, 5 endpoints. So notice for midpoint rule, n equals 4, you have 4 midpoints, 4 calculations. For the trapezoidal rule and the Simpson's rule, if n is 4, you're going to have 5 calculations. Simpson's rule, n equals 4, 5 calculations. In general, if you have chop it up into n pieces, for trapezoidal rule and Simpson's rule, you will have n plus 1 calculations. Okay, so remember that thing I showed you before the break, right? It's at delta x over 2, and then 1, 1, 2, 2, 2, 2, 2, right? Here's the way it works. 1 goes here, 1 goes here, and you don't actually have to write it if you don't want to. But the concept is you multiply the first and last ones by 1, and then all the in-between guys get a factor of 2. Simpson's rule, 1, 1, and then you alternate 4, 2, 4. Remember that the second number and the second to the last number are multiplied by 4. Okay, so here's the way it works. Delta x over 2. Don't use the midpoints, just these endpoints. F of 0, f of 1/4, f of 1/2, f of 3/4, and f of 1. F of 0, 1/4, 1/2, 3/4, and 1. And now the multiplication factors. Multiply the first one and the last one by 1. Yeah, you're right. You don't really have to put it because when you multiply by 1, it stays the same. And all the in-between ones get multiplied by 2. So 1, 2, 2, 2, 1. So it's 2 times f of 1/4, 2 times f of 1/2, 2 times f of 3/4, and then 1 times f of 1. So it's 1 over 8 this time. Okay, delta x is 1/4. 1/4 divided by 2, which is the same as 1/4 times 1/2, is 1/8. So multiplying by 1/8. So it's 1 times e to the 0 plus 2 times e to the 1/4 squared is e to the 1/16. Plus 2 times e to the 1/2 squared is e to the 1/4. Plus 2 times e to the 3/4 squared is 9/16. And then 1 times e to the 1. Okay, 1/8 is half of 1/4. So for trapezoidal rule, delta x divided by 2, 1, 2, 2, 2, 2, and then 1. So 1 times this one, 1 times that one. All the in-between ones get multiplied by 2. And in front of the whole thing is delta x divided by 2. Okay. This is by making all of these into trapezoids. Making a trapezoid here, and a trapezoid here, and a trapezoid here, and a trapezoid here. Okay, punch in your calculator, 1.490679. And you can do that. Just make sure you can get the same number as I got. Rounded to 6 digits. 6 digits. And by the way, just notice these two numbers. Okay, kind of close. I would not expect them to be exactly the same, although it's possible. But they're kind of close. And it kind of makes sense also because we're using different geometric objects. Here, we're doing a bunch of rectangles. Here, we're doing a bunch of trapezoids. So they're close. Which one's a better approximation? No idea. Okay. But it does seem reasonable that, all right, they're kind of close. All right, number 2, trapezoidal rule. Same function. Same end, same interval. But this time, I don't need the midpoints. I just use the endpoints. Okay, so these numbers are the same, 1 and 1/8, 1 and 2/8, 1 and 3/8, 4/8, 5/8, 6/8, 7/8, 8/8. Okay, there were 8 midpoints. How many endpoints are there? There should be one more than 8 or 9. So you have 9 calculations. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the calculations in here, there should be 9 of them. Let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So T8, delta x over 2. What was delta x in this case? It was 1/8. Divide that by 2, 1/16. Right? 1/8 times 1/2 is 1/16. Okay. 1 times f of 1, 1 times f of 2, and all the in-betweens are 2, 2, 2, 2, 2, right? 2 times that, 2 times that, 2 times that. So here we go. 1 times f of 1, the first one. 1 times f of 2, the last one. And all the in-between guys get multiplied by 2. So let's see. So 2 times f of 1 and 1/8, which is 9/8. 2 times f of 1 and 1/4. 2 times f of 1 and 3/8, or 11/8. 2 times f of 1 1/2, or 3 over 2. 2 times f of 1 and 5/8, 13/8. 2 times f of 1 and 3/4, 7/4. 2 times f of 1 and 7/8, 2 times f of 15/8. And now that I reach the last one, 1 times f of 2. Okay, so again, trapezoidal rule, delta x over 2, 1 at the beginning, 1 at the end, and all the middle ones get 2, 2, 2, 2, 2, 2, 2. Okay, so the function is x cubed. So f of whatever is that thing cubed. So here we go. Delta x over 2 is now 1/16, 1 cubed. And notice all the in-between ones get 2, 2, 2, 2, 2, 2, 2, 2, and then the last one only gets a 1. And yeah, you don't really need to write the 1 at the end, but I just put it. Okay, and then you're cubing all these. The function is x cubed. So you cube 9/8, 5/4, 11/8, 3/2, 13/8, 7/4, 15/8, and 2. The last one was 2. Okay, I'm not actually going to do it. I did it before. Just punch it in your calculator. 3.761719. So this is the trapezoidal rule. And a side note, look at the exact answer, 3.75. So this was pretty good, right? In fact, this looks better than that. That's still pretty good, but 3.76 seems to be a little bit better for the exact value. All right, so that's a trapezoidal rule. And now Simpson's rule, same principle. Okay. Notice, by the way, here, n is 4, but you have 1, 2, 3, 4, 5 calculations, 5 endpoints. N is 8. There were 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 calculations. So there's always going to be one more calculation for the trapezoidal rule. And the same thing for Simpson's rule. In fact, if you understand the trapezoidal rule, Simpson's rule is the same thing. Instead of delta x over 2, it's delta x over 3, and we know what the coefficient should be. Okay. But for this midpoint rule, n is 4 midpoints, 4 calculations. N equals 8 midpoints, 1, 2, 3, 4, 5, 6, 7, 8. But here there's going to be 9 calculations. Here there's going to be 9 calculations. Here n is 4, 5 calculations, 5 calculations. Okay, so just before the break, for Simpson's rule, okay, what's happening for Simpson's rule is you're making the best parabolic approximation, parabola. So take these 1, 2, 3, draw a curve, parabola. 1, 2, 3, draw a parabola. You can see it's a pretty good approximation. So it's delta x over 3. So midpoint rule, delta x over 1. Trapezoidal, delta x over 2. Simpson's, delta x over 3. We say S4, Simpson's rule, n equals 4. So 1, 2, 3, 4, 5 pieces. Just like a trapezoidal rule, multiplication factor is 1. Multiplication factor is 1. And then in between, you go 4, 2, 4, and then 1. And if you do it the right way, the second number is a 4, and the second to the last one should also be a 4, as it is. That only works if n is a even number. Okay, so 1 times f of 0, and then 4 times f of 1/4, plus 2 times f of a half, plus 4 times f of 3/4, and then 1 times f of 1. You don't need the midpoints, right? So trapezoidal rule, no midpoints. Simpson's rule, no midpoints. Where's the only case where you need the midpoints? Midpoint rule, logical. So these, no midpoints, just the endpoints, of which in this case there are 5. All right, so delta x was 1/4. Divide that by 3. So 1/4 divided by 3 means 1/4 times 1/3, or 1/12. Okay, so delta x over 3 is 1/12. 1 times e to the 0. And notice it goes 4, 2, 4, 1. So 4 times, in fact, these e's are going to be same as these. E to the 1/16th, same thing, e to the 1/16th, e to the 1/4, e to the 1/4, e to the 9/16th, e to the 9/16th, and then e to the 1 are just e. So 1/12, 1 e to the 0, plus 4 e to the 1/16th, plus 2 e to the 1/4, plus 4 e to the 9/16th, plus 1 times e. Okay, punch it in the machine, 1.463711, round it to 6 decimal places. Okay, make sure when you try this on your home later, you get the same numbers. Okay. All right, and let's compare. Midpoint rule, 1.44 something. Trapezoidal rule, 1.49 something. Simpson's rule, 1.46 something. Okay, so they're all pretty close. So we suspect the true value is somewhere in that neighborhood of 1.4 or whatever. Problem is we don't know how to integrate this, so we can't get this exactly. So the only thing we can do are just approximations like this. Okay, same thing here. So number 2, y equals x cubed. From 1 to 2, n equals 8. So don't need the midpoints. Notice I have the midpoints here. Don't need it here. Don't need it here. Here you go, 1, 1, 2, 2, 2, 2, 2, 2, 2. Here you go, 1, 1, and now follow this, 4, 2, 4, 2, 4, 2, 4, second to the last one, perfect, and it's a 1. Okay, so if you do it the right way, the second numbers are 4 here, second to the last number is 4. So if you don't get that, then something went wrong. And again, that only works for even numbers. As you might guess, if there's an odd number, then the numbering is off. Okay, so again, 1, 1, then you alternate, 4, 2, 4, 2, 4, 2, 4, and then 1. All right, so S8 means Simpson's rule, 8 pieces. Trapezoidal rule, 8 pieces. Midpoint rule, 8 pieces. Midpoint rule, 4 pieces. Trapezoidal rule, 4 pieces. Simpson's rule, 4 pieces. Okay, so delta x over 3. Use the same endpoints here as here. So Simpson's rule, trapezoidal rule, you use the same points, only these endpoints. Don't use the midpoints. When do you use the midpoint rule? When you're doing midpoint rule, right? So only for midpoints. So delta x over 3, so it's 1/8. Delta x is 1/8. Divided by 3 is 1/24. Okay, so 1 times f of 1. And now you have the same function values at 9/8, 5/4, 11/8, 3/2, same as these. 13 over 8, 7 over 4, 15 over 8, and 2. So these match. F of 1, 9/8, f of 5/4, f of 11/8, f of 3/2, f of 13 over 8, f of 7 over 4, f of 15 over 8, f of 2. The coefficients, 1 at the beginning, 1 at the end, 4, 2, 4, 2, 4, 2, 4, second to the last one's a 4, and then a 1. Perfect. Now I throw it into the function. What's the function? X cubed. So 1 cubed, 4 times 9/8 cubed, 2 times 5/4 cubed, 4 times 11/8 cubed. Notice these are all the same as these, right? 1, 9/8, 5/4, 11/8. The only difference is the coefficient. These are all 2's, we said, right? But here you go 4, 2, 4. 2 times 3 over 2 cubed. 4 times 13 over 8 cubed. 2 times 7 over 4 cubed. 4 times 15/8 cubed. 1 times 2 cubed. Punch it in the calculator, 3.75. Okay. And do you notice anything about that answer? We did it by actual integration, 3.75. So Simpson's root gave us the exact same answer. Now that's not always going to happen, but usually that's true. Usually Simpson's root is the best. And then these two are close, right? So these are kind of close, I suppose, but off by a little bit for both of these. Okay. All right, so that's 1 and 2. Okay, what time is it? 8:50-ish? Okay, so I wanted to show you, for 1 and 2, I wanted to show you 2 midpoints, 2 trapezoidal, and 2 Simpsons. Okay, last one I'll show you is number 4, and I'll do all 3 at the same time. So y equals sine x between 0 and 2 pi, and is equal to 8. Okay. Okay, y equals sine x between 0 and 2 pi, and equals 8. Here's the actual graph. Okay. Before we do this, by the way, do we know how to integrate sine? Yes, we do. Integral of sine is negative cosine. So we can figure this one out exactly. Or you can just look at the picture. Remember from Calc 1, right? By symmetry, I have exactly the same amount of area above as below, which means the area should be, or the net area, I should say, is 0. Okay, and if you look all the way down here, integral from 0 to 2 pi of sine x dx. We can't find the exact value. Integral of the sine is negative the cosine from 0 to 2 pi. So the negative of cosine of 2 pi, it's the same as the cosine of 0. That's 1 revolution, so it's 1. So negative 1 minus 1, which is equal to 0. So we're expecting 0 as the exact answer. Okay. So let's see what happens when I do each of these. Okay, midpoint. Okay, chop this interval from 0 to 2 pi into 8 pieces. Oh boy. So it's 2 pi divided by 8, which is pi over 4. Okay, so this is kind of clumsy. Pi over 4, 2 pi over 4, which is pi over 2, 3 pi over 4, 4 pi over 4, pi, 5 pi over 4, 6 pi over 4, 3 pi over 2, 7 pi over 4, 8 pi over 4, which is 2 pi. I need all the midpoints. To find the midpoints, let's get all these denominators to be 8. Okay. 2 pi over 8, 4 pi over 8, 6 pi over 8, and so on. So what's halfway between 0 and 2 pi over 8, pi over 8. Okay, this is 2 pi over 8. Pi over 2 is 4 pi over 8. So what's halfway? 3 pi over 8. And you can kind of get the pattern. After that, just take the odd coefficients. So the midpoints are pi over 8, 3 pi over 8, 5 pi over 8, 7 pi over 8, 9, 11, 13, and 15 pi over 8. Okay, so those are the midpoints. How many midpoints are there? 1, 2, 3, 4, 5, 6, 7, 8. My n is 8. Okay, so the number of midpoints matches the n, but for the trapezoidal rule and Simpson's rule, there's going to be one more. So if you have n pieces, you have n plus 1 endpoints for both the trapezoidal rule and Simpson's rule. Okay, midpoint rule M8, delta x, or I put delta x over 1, which means don't do anything. And in that thing I showed you just before the break, it was 1, 1, 1, 1, 1, which means don't multiply by anything, just leave it alone. So f of all the midpoints, f of pi over 8, f of 3 pi over 8, f of 5 pi over 8, f of 7 pi over 8, f of 9 pi over 8, f of 11 pi over 8, f of 13 pi over 8, f of 15 pi over 8. So these are the 1, 2, 3, 4, 5, 6, 7, 8 midpoints. Okay, what is the function? Sine. So I punch it in the sine. Make sure you are in radian mode. So if you're in degree mode, change the radians. So pi over 4, sine of pi over 8, plus sine of 3 pi over 8, plus sine of 5 pi over 8, plus sine of 7 pi over 8, plus sine of 9 pi over 8, plus sine of 11 pi over 8, plus sine of 13 pi over 8, plus sine of 15 pi over 8. Punch it in the calculator. Believe it or not, it comes out to be 0. So the midpoint rule this time gave us the exact value, 0. Pretty good. All right. Trapezoidal rule, T8. Midpoint rule is delta x over 1. This is delta x over 2. So what's half of pi over 4? Pi over 8. Okay, don't use the midpoints. Use the 1, 2, 3, 4, 5, 6, 7, 8, 9 endpoints. Okay, so don't use any of the red numbers. Just these 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1 times f of 0, 1 times f of 2 pi, all the in-between ones multiplied by 2. 2, 2, 2, 2, 2, 2, 2, and then 1. So again, trapezoidal rule, delta x over 2, which in this case is pi over 8. Half of pi over 4 is pi over 8. So f of 0, and then 2 times sine of pi over 4, 2 times sine of pi over 2, 2 times sine of 3 pi over 4, 2 times the sine of pi, 2 times the sine of 5 pi over 4, 2 times the sine of 3 pi over 2, 2 times the sine of 7 pi over 4, and then 1 times the sine of 2 pi. Okay, you could punch it in your calculator, but actually everything cancels out. Okay, let's see if I can convince you of that. Okay, sine of 0 is 0, sine of 2 pi is 0, sine of pi is 0. So that's nothing, that's nothing, that's nothing. Let me just cover them. So now I have these 6 numbers. Let's look at this. What's the sine of pi over 2? 1. What's the sine of 3 pi over 2? Negative 1. So they cancel out. Okay, and you get a cancellation here also. Sine of pi over 4, radical 2 over 2. Sine of 5 pi over 4, negative radical 2 over 2. These cancel out. Same thing here. Sine of 3 pi over 4, radical 2 over 2. Sine of 7 pi over 4, negative radical 2 over 2. These cancel out. So once again, you get 0. Now, if you didn't like any of that, you want to punch it all in your calculator, fine, you get 0. Okay, but for those of you that just want to get it off of trig, okay, sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0. So those are all gone. And it turns out the way I wrote it is that that cancels that one out, that cancels that cancels that. So we get 0. And then if you multiply by pi over 8, it doesn't matter, it's still 0. Okay, well, let's see. That came out to be 0, midpoint rule. That came out to be 0, trapezoidal rule. The exact answer is 0. We said Simpson's rule tends to be the best. So all of those conspire to lead us to believe Simpson's rule should come out to be 0. And let's see if that's the case. Okay, Simpson's rule, delta x over 3. So remember that thing I showed you before the break? So midpoint rule, delta x over 1. Trapezoidal rule, delta x over 2. Simpson's rule, delta x over 3. Put it on your cheat sheet if you wish. Okay, n is 8. So how many calculations are there? Not 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1 here, then follow along. 4, 2, 4, 2, 4, 2, 4. Perfect. Second to the last one is 4, and then a 1. Okay. So again, the second number is always a 4. Second to the last one is 4. So if it doesn't come out that way, something went wrong. Okay. So 1, 4, 2, 4, 2, 4, 2, 4, 1. Okay, so I have delta x over 3. That's pi over 4 divided by 3 is pi over 12. So 1 times f of 0, 1 times f of 2 pi, and then all the in-between ones, 4, 2, 4, 2, 4, 2, 4, and then 1. Not the midpoints, just these endpoints. Pi over 4, pi over 2, 3 pi over 4 pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, 2 pi. So here we are. F of 0, 4 times f of pi over 4, 2 times f of pi over 2, 4 times f of 3 pi over 4, 2 times f of pi, 4 times f of 5 pi over 4, 2 times f of 3 pi over 2, 4 times f of 7 pi over 4, 1 times f of 2 pi. Okay, well, basically the same thing happens. Okay, so it's 1 times sine of 0. This is a sine function, right? So 4 sine of pi over 4, 2 sine of pi over 2, 4 sine of 3 pi over 4, 2 sine of pi, 4 sine of 5 pi over 4, 2 sine of 3 pi over 2, 4 sine of 7 pi over 4, 1 sine of 2 pi. And just like before, right? That's 0, that's 0, that's 0. So forget about these. Sine of pi over 4, radical 2 over 2. Sine of 5 pi over 4, negative radical 2 over 2. Multiplied by 4, they cancel out, that's 0. Sine of pi over 2 is 1. Sine of 3 pi over 2 is negative 1. Multiplied by 2, multiplied by 2, they cancel out. Same thing here. Sine of 3 pi over 4, radical 2 over 2. Negative radical 2 over 2, sine of 7 pi over 4, multiplied by 4, they cancel out. So all of them are 0. And the true value turns out to be 0. So here's an instance where all 3 methods gave you the exact value, which came out to be 0. Okay, so there we go. Okay, it's about 9 o'clock, so I'm done, folks. So I've shown you all I wanted to for 7-7. There are 6 problems. I did exactly half, 1, 2, and 4. So you do 3, 5, and 6 on your own later. Okay, and again, schedule-wise, I'm done with 7-4, folks. So, sorry, I'm done with 7-7. So actually what I should do is check this off. So I have to be careful about using this language. We could afford to skip Thursday, but I'm not going to do that. Okay, if I took a holiday on Thursday, we'd be just on par, but I'm not going to do it. Like I said before, I want to get ahead in case something goes wrong again, quote unquote. I never know if that's going to happen. So I will get started with 7.8 on Thursday, and I'll give you a quiz on Thursday. Most likely it'll be stuff from 7.3 and 7.4. Okay, so let me stop the share and check the chat. Okay. Do we have to show all 3 rules when doing these questions? Yes. On the exam, that might take very long. So on the exam, I might just have you show one of them. Or if I have you show all three, it may be just something very easy that you can do all three. So most likely on the exam, I might say only do trapezoidal rule or only do Simpson's rule or something like that. Do we have to draw the function graph for 7.7? No, in general you don't. Notice I didn't do it, right? The only one I drew was number 1, but all the others I didn't draw the graph. I take it back, I actually drew the sign, but I didn't draw the rest. You do have to show your table for delta x's. Remember I showed you all the delta x's? So you do want to show me that there. Okay. All right, folks, it's a little bit past 9. I'll take questions if you have any, but if not, we can stop and we can just call it a day since I'm a little bit ahead. Okay, so you can either unmute yourselves or put it in the chat. So anybody want to ask me something, please?
I have a question about 7.4, number 15.
7.415?
Yes.
Okay.
Just for the final answer for that, are you looking for us to, you know, just go ahead and simplify that, or will you take like a -3 ln3 minus the ln2?
Yeah, so about negative ln3 and minus ln2. Anytime you can combine the ln's, you should, since we have a way of doing it. And the whole idea behind simplification, right? So if you just have a single ln6, that's considered easier than having, you know, an ln3 and an ln2. Now, if you got all the way to that part, I'd probably give you 9 out of 10, right? But just that, but technically, I mean, it's almost like the same thing as, do you leave an answer as 3 plus 2? No, you should change it to 5, right? So if you have a minus ln3 and a minus ln2, there is a way to combine it, so you should combine it. Okay, just like you leave your answer as 3 plus 2. No, you should leave it as 5.
Right, and would you take it as just ln3 over 2? You know,
ln3 over 2. If the final answer came out that way, yes, that'd be
yeah,
fine.
yeah.
That'd be also okay.
Okay.
All right. Okay, let's see. I think I'm clear on the chat. So anybody else with something, you can either unmute yourselves or put it in chat. Anything else, please? No? Okay, then we're done, folks. All right, so I will get started with 7.8 next time, which is our last section. So I'm a little bit ahead, and we will have a quiz, most likely on 7.3, 7.4, second half. Same thing, I'll give you the question, take a picture, and then I'll break you up into your breakout rooms, and it's due the following Tuesday. Okay. All right, that'll do it for tonight, folks. So have a good evening, and we'll see you next time. Okay, bye, everybody. Good night.